Hello everyone, this video is going to go over the Unit 1 practice test for Physics 251 in detail. Number 1, a diver stands on a diving board, bounces to create an oscillation, then swan dives into a swimming pool. Draw a motion diagram for the diver after they leave the diving board, use 6 to 8 dots and sketch in the appropriate velocity vectors. Graphically calculate the magnitude and direction of the acceleration vector at the highest point in the diver's trajectory. Okay, so you don't have any guidance about exactly what the launch angle is or what the initial velocity is, but you do know that the diver is going to act like a projectile after they leave the diving board. So you can start off with pretty much any position for time is equal to 0. And once you make a decision about what your V0 velocity vector looks like in terms of magnitude and its direction, then you can just determine which of the components, X or Y, is going to stay the same and which one is going to change. So for a projectile, the acceleration in the X direction is equal to 0. So that means that I move the same number of blocks over to the right between every adjacent pair of dots, but the vertical component of the velocity is going to shrink as you go to the highest point in the trajectory. And that occurs for me at t is equal to 3. Again, these are the initial position and the initial velocity vector are arbitrary. So it's okay if you drew a motion diagram that is not identical to mine, but still follows the same rules. So I move over 5 blocks to the right for every second of time that the diver spends in the air. At t is equal to 3, the velocity vector's vertical component would be equal to 0. And then from t is equal to 3 down to t is equal to 6, the diver is accelerating toward the pool. So the vertical change in the, number of blocks that I selected for the velocity vector between time 2 and 3 should be the same number of blocks I count down for 3 to 4. Likewise, the number of blocks vertically that I went up between 1 and 2 should be the same that I go down between 4 and 5, and so on. Now for the next part, let's shrink this a little bit. We have a velocity vector, or we want the acceleration vector for the highest point in the trajectory. So for me, I would need to take velocity vector v3 and subtract vector v2 from it. So I've done that down here where negative v2 just has the same magnitude as my original velocity vector v2, only the direction is different by 180 degrees. And what I end up with is a vector that I have labeled as acceleration, but it would also be valid to label this as the vector delta v. It's the difference between v final and v initial. The delta v vector and the acceleration vector always point in the same direction. Number 2, consider the graph below. Assume that this object begins at the origin. Determine the position of this object at the end of the 15-second interval. So we have a velocity versus time graph where for 5 seconds, the velocity increases from 0 meters per second to positive 5 meters per second. Then for 5 seconds, it just maintains a velocity of positive 5 meters per second. And over the next 5 seconds, it goes from positive 5 meters per second to negative 5 meters per second. So there's more than one way to solve this problem, and I've shown 2 examples here in the solution document. This first one involves computing the slopes of the sections of the graph because since this is a velocity graph, the slope will give me information about the acceleration. So between 0 and 5 seconds, the slope is positive 1 meter per second squared. I can take that slope and recognize that it is going to be the acceleration for the interval from 0 to 5 seconds. And I'm using a kinematic equation for position. S final is equal to S initial plus V initial S times delta t plus half the acceleration in the S direction times delta t squared. Because I know that this object starts at the origin, I know S initial is equal to 0. The initial velocity at time 0 is also 0 meters per second, so I can fill that in there. And I can plug in the acceleration and then 5 seconds for delta t. That tells me that at t is equal to 5 seconds, this object has a position of 12.5 meters. Next, I can look at the second section between 5 and 10 seconds. The slope there is 0 meters per second squared, so that means that the velocity of this object is just going to be constant over that 5-second interval. I can still use the same kinematic equation for position, only what was the final position in the previous step is now going to be the initial position in the next step. At t is equal to 5, the beginning of that second interval, the velocity is positive 5 meters per second. So I can plug that in there for v initial. The object is moving in this fashion for 5 seconds, and I can plug in a 0 for the acceleration because that section of the velocity graph is horizontal. That tells me that at t is equal to 10 seconds, this object is now 25 meters further away, so it's at 37.5 meters. And then finally, the slope for the section between 10 and 15 seconds is negative 2 meters per second squared. So v final is negative 5, v initial is positive 5. So negative 5 minus positive 5 is going to give 10. And you've got a 5-second interval here, so that's where my negative 2 meters per second squared comes from. So I can use that for the acceleration over the last section, where the final position from the middle step becomes the initial position for the last step. I plug in 5 meters per second for the initial velocity at t is equal to 10 seconds, because that's what is indicated on the graph. And then I can just plug in the acceleration with the negative sign. And what I find is that over the interval between 10 and 15 seconds, the object rolls or moves forward, then moves backward by exactly the same amount. So I'm adding 25 and then subtracting 25, so that at t is equal to 15, the object is at 37.5 meters. The other way you can do this is to compute the area below the curve. So this is exactly the same graph, split up into pieces. Now going from 0 to 5 seconds, 5 to 10, I have 10 seconds to 12.5 seconds, and then 12.5 to 15, because I can see that the velocity of this object is going to be 0 meters per second at exactly 12.5 seconds. Okay, so I've got a group of triangles and rectangles. This first one has a width, or like a base, that's 5 seconds wide. It's got a height of positive 5 meters per second, such that 1/2 5 seconds times 5 meters per second gives you a displacement of 12.5 meters over that 5-second interval. Next, take the area of the rectangle that's 5 seconds wide and 5 meters per second tall for an additional 25 meters of displacement. From 10 to 12.5, the base is now only 2.5 seconds long, and the triangle is positive 5 meters per second tall. So 1/2 of that product gives you 6.25 meters. And then finally, 12.5 to 15 seconds, I have a triangle that has exactly the same dimensions, only the velocity is now negative 5. So that is negative 6.25 meters over that interval. If you add all of those quantities together, you have the same total displacement as what we saw with the previous method. So it demonstrates that both of those methods will work. Whichever one makes the most sense to you is the one that you should stick with. Number 3, we have vectors that are described in unit vector notation. A is 3.6 I hat plus 2.5 j hat. Vector B is negative 1.7 I hat plus 4.6 j hat. Vector C is negative 0.8 I hat minus 9.0 j hat. And we want the sum, vector D, that's equal to 5 times the sum of vector A and B minus 2 times vector C. Okay, so what we can do is first add vector A and B together. So I'm just taking the x components and adding them. So positive 3.6 plus negative 1.7 in the I hat direction. Positive 2.5 plus positive 4.6 in the j hat direction. I get the vector AB that is positive 1.9 I hat plus 7.1 j hat. Taking that and multiplying it by 5 gives me 9.5 I hat plus 35.5 j hat. And finally, I can take vector C and multiply it by negative 2. So that's negative 2 times negative 0.8 I hat. That yields a positive 1.6 I hat. And then negative 2 times negative 9.0 j hat, which is going to yield a positive 18 j hat. And all I have to do is add these together because I have the vector 5 plus 5 times the vector A plus B added to vector negative 2c. And what you end up with is vector D, that is 11 I hat plus 54 j hat. So the magnitude and direction of vector D can be determined just by determining what the component vectors would look like for vector D. So positive 11, that means that 11 units along the positive x-axis would comprise my component vector dx. dy would be 54 units along the positive y-axis, so vector dy. And using the abbreviated parallelogram method here, vector d would look like this. And we are asked to express the angle with respect to positive x. So I'm going to call this angle theta. And then I can use an inverse tangent to figure out what theta is. So the inverse tangent of 53.5, which is my unrounded value, over 11.1, which is the other unrounded value. And you get an angle of 78.279 degrees. And applying sig figs, you would have 78 degrees for that angle. Number 4 is a similar problem. A drone rises 3.0 meters straight up, travels 2.6 meters directed 28 degrees south of west, 7.3 meters directed 19 degrees east of north, then travels 4.5 meters due east. You can describe these maneuvers as position vectors. So I've just chosen R1 to represent the 3.0 meters straight up. So since we're talking about cardinal directions in addition to motion straight up, I know this 3.0 meters is going to be expressed along the positive z-axis. So that is in the k hat direction. Nothing is happening in the I hat or j hat direction. For maneuver 2, 2.6 meters directed 28 degrees south of west. I've drawn that vector here, where I start by just pointing west and then sweeping down 28 degrees south. And this hypotenuse is 2.6 meters. So that's going to be 2.6 meters times the cosine of 28 degrees to capture the x component of this vector. And it points toward negative x, so I have a negative sign here. And if I look at the y component, that's going to be 2.6 meters times the sine of 28 degrees. And that also needs to be expressed as a negative because this y component points straight down, so toward the negative y-axis. So that's negative 2.6 sine 28 in the j hat direction. But this is just happening in a plane that's parallel to ground level. So the drone is not moving up or down at all while it's carrying out that maneuver. I'm adding a 0 k hat. Likewise, for maneuver 3, 7.3 meters directed 19 degrees east of north. First, I start with a vector that represents north, add one that represents east, and the angle that's subtended is the 19 degrees. And I know that the hypotenuse is 7.3 meters, so I can split that into sine and cosine components just as I did before. However, since the 19-degree angle is expressed with respect to the y-axis, R3's x component is going to be 7.3 sine 19 because the sine is communicating the opposite portion. So it's not safe to say that cosine is always x and sine is always y. Here's an example where it's reversed. 7.3 cosine 19 is equal to the vertical component. That's positive, so it's going to be a positive. Nothing's happening in the z-axis, so I have a 0 k-hat. And then finally for maneuver 4, it's just 4.5 meters due east. So due east just means in the positive x direction. So I have 0 j-hat, 0 k-hat. I can take the sum of all of these, that's going to be r net. So I can just grab all of the I-hat components, 0 minus 2.6 cosine 28 degrees, plus 7.3 sine 19 degrees, plus 4.5. And I can do the same for the j-hat and the k-hat direction. And I'm just going to be adding zeros to that k-hat component that comes from R1. So I know I'm going to still have 3.0 k-hat at the end there. My unrounded net displacement vector components are shown here. But to determine the magnitude, I need to take the square root of the sum of the squares of each component. So in other words, this is the x component squared added to the y component squared added to the z component squared, all of that underneath the square root. When you carry that out, you get 62.2667 square meters. And taking a square root will take you to 7.8909 meters. Applying sig figs, that gets you to 7.9. Number 5, this is a projectile motion question. A loaded canyon is positioned at the edge of the Grand Canyon, which is 1.83 kilometers deep. The cannon is set 45 degrees above horizontal. The ball exits with an initial velocity of 50 meters per second. A target is placed on the canyon floor, 750 meters to the right of the ball's release point. Will the ball hit the target? If it doesn't, indicate its location with respect to the target. We are ignoring air resistance, which is something that you can assume to be the case anytime you're not told anything to the contrary. So the initial position in the coordinate system that I'm choosing, I'm going to say that the bottom of the canyon is y is equal to 0. So that means that the initial position that the cannonball has is going to be positive 1,830 meters. I'm going to say that the origin of the coordinate system is right below the release point such that x initial is going to be 0 meters and x final is going to be where this cannonball hits the ground. You know it will happen eventually, but what we don't know is whether it's going to land right on top of that target. I have a launch angle of 45 degrees. So V initial x and V initial y are going to be the same value, at least in terms of magnitude in this case. So 50 meters per second times the cosine of 45 degrees is V initial x. 50 meters per second times sine 45 degrees is V initial y. Now, the cannonball is going to be moving in the air for the same interval of time that it's moving. It's moving horizontally for the same time it's moving vertically. So I can use the vertical kinematic equation to figure out what delta t is. You can start there. You could also technically determine how much time the cannonball would have to be in the air in order to hit the target. That's at 750 meters, but that would just give you a delta t that you could plug into the vertical position equation and see whether it made sense. And I think it makes a little bit more logical sense to figure out the flight time and then to use that to figure out the position. So I just plug in what I know. V initial y is just the sine component of 50 meters per second. And my coordinate system means that my initial vertical velocity component is positive. The acceleration is going to be a negative. You get two roots where the negative one can be discarded and the positive one is the meaningful one, 23.27 seconds. Next, that's exactly the same amount of time that the cannonball is moving horizontally. So because this is a projectile motion problem where air resistance is negligible, the acceleration in the x direction is equal to 0. The x kinematic equation just becomes x initial plus v initial x times delta t. I know v initial x is the cosine component of the initial velocity, and I know the flight time. So I end up with a position of 822.61 meters. So that's not 750 meters. I can figure out where the ball lands relative to the target, and I find that it overshoots by 73 meters. Number 2, a bike tire with a 66 centimeter diameter spins with an initial angular velocity of 50.0 revolutions per minute. It's then allowed to slow to a stop over a 30-second interval. What's the tangential speed of a pebble lodged in the tire's tread before the wheel begins to decelerate? Okay, so we can start with the angular velocity that we're given. It's in RPM, or revolutions per minute. And in order to figure out what the tangential speed is in meters per second, which is the SI unit that we want, we can start by just converting 50 RPM, or 50 revolutions per minute, into radian per second. So if a single revolution is 2 pi radian, and if a single minute is 60 seconds, I can multiply across the top, divide by the product of everything on the bottom, and that leaves me with 5 pi over 3 radian per second. It would be fine if you wrote a decimal approximation of this. Now that we know what omega is in the appropriate units, we can use our tangential speed equation. So V tangential is omega times r, where r is the radius in meters. So instead of 66 centimeters, cut that in half to make it 33 centimeters, then convert it to make that 0.33 meters. Multiplying those two gives you the tangential speed, 1.7 meters per second. So a pebble that is 33 centimeters away from the center of this wheel would have the same tangential speed. Next, for part B, calculate the angular displacement of the wheel during its period of deceleration. So I know it takes 30 seconds to come to a stop. I don't have the angular acceleration value, but I can figure that out because I have the initial angular velocity in the appropriate units, 5 pi over 3 radian per second, and I know that eventually the final angular velocity is going to be 0. So delta omega would just be negative 5 pi over 3 radian per second. I can divide that by the 30-second interval, and you get negative pi over 18 radian per second squared. Again, it's fine to write the decimal approximation of this as well. And once you know alpha, there are 2 ways you can answer the question of how many times it actually turns. So the angular displacement of the wheel while it's decelerating. One involves the time-dependent kinematic equation for position. I'm subtracting theta initial over so that I have a delta theta, but it would be equally valid just to say that theta initial is 0 radian. The initial angular velocity is 5 pi over 3 radian per second. The time it takes to decelerate is 30 seconds, and we've just figured out what the acceleration is, alpha. Negative pi over 18 radian per second squared. Carry that out, you get 25 pi radian, which is approximately 78.54 radian. So you can round that to 79 when you apply sig figs. But that was just one of 2 methods we could use. We also have enough to figure out what delta theta is using the time-independent kinematic equation. So the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement, delta theta. I know all of these values. I also know that alpha is a negative value. That's going to be relevant because when you take omega initial squared and subtract it to the other side, you're going to end up with either 2 negatives that cancel, or you can add your 2 times negative pi over 18 times delta theta term to the other side. No matter what, you're going to end up with cancellation here. 9 is going to cancel 9. This should be 25 pi radian. I wrote a 25 here, but just didn't write it there. But that is the same answer. So the method that you use doesn't matter. 7. A camper wants to paddle a canoe across a river that's 50 meters wide. The river flows 1 meter per second east relative to Earth. The camper can paddle with a speed of 1.5 meters per second relative to the water. Determine the direction the camper should choose in order to land directly across from the initial position and the amount of time that it takes to cross the river. All right, so this is sort of like the problem we solved in class in that we know the speed of the canoe relative to the water, and we're trying to choose an angle theta such that the sine component of v canoe is exactly enough to cancel out v river. In other words, we want our velocity vector to break down like it's doing here on the right-hand side. V canoe is the hypotenuse, so the y component that takes you directly across the river would be v canoe cosine theta. The x component that needs to cancel out v river is v canoe sine theta. So if those magnitudes are the same, then I can plug in the velocity of the river relative to the bank, which is positive 1.0 meter per second. I can divide that by the velocity of the canoe relative to the water, which is 1.5 meters per second, and then compute the inverse side. And doing that yields 41.8 degrees. So to 2 sig figs, that is 42. You know how to angle the canoe now. To determine the amount of time that it takes for this trip to complete, you just need to figure out what the time interval is for this 50-meter distance if the velocity is equal to v canoe cosine theta. So we know what theta is now. So v canoe cosine theta is just going to be 1.5 meters per second times the cosine of 41.8 degrees. And we're plugging that into our velocity equation that we have rearranged to solve for delta t. So the displacement delta s is the 50-meter width of the river, and v canoe cosine theta is the denominator of this statement down here. When we do that, you get 44.7 seconds, which would round to 45 seconds when you apply sig figs. And then finally, here's another type of problem that we can solve that is similar to the one that's previous. If instead the camper launches perpendicular to the southern bank, how far downstream will the canoe be when it reaches the other side? So you're no longer trying to use some component of v canoe to cancel out v river. Now you're just using the entire 1.5 meters per second so that it's oriented along the vertical axis. But just as we saw before with part B and also with every projectile motion problem, the delta t that we calculate for the trip across the river in the northward direction is going to be exactly the same time that the canoe moves horizontally or from west to east. So I can figure out what that delta t is by taking delta s, the width of the river, divided by the entirety of the canoe's speed relative to the water, because it's not being angled this time. That's 33.3 seconds. And now the delta S that I have designated here is the unknown. So the quantity that is marked with the question mark, we could call this delta X, but I have a delta S written here, so this is the formula just in its general form. So the velocity of the river relative to the bank is all that's capable of carrying the canoe downstream. So 1.00 meters per second is valid here. We know the trip lasts 33.3 seconds. Therefore, the distance traveled in that time would be 33.3 meters.